Welcome everyone. Today we have Matthew Leung from Rutgers talking about second moment of algebraic cusp form alpha.
Great. Yeah, thanks. Thanks for the invitation. It's always good to be here. I'll be around a lot more often now that I'm on the road, off the road. Yeah, before I forget, so this is joint work with Agniva Dasgupta and or Joseph Leung. So Agniva was my PhD student, and Joseph is my the postdoc at Rutgers. So I wanted to try to start with like a really accessible beginning. So the basic question that we might be interested in is what's the distribution of the Riemann zeta function on the critical line? And so I've found a plot of so what this is the Hardy Z function. So this is a function that's real valued, and it has the same absolute value as zeta. And so this is okay. I can't quite see. Okay, maybe if I'm here. So this is up to 30. And then this is up to 100. This goes up to, this is 4 right here. Can't see that. So here this is up to 1,000, and the scale is up to 10, and then this is 10,000, and it's up to 15. So this is supposed to indicate that this Z function is oscillatory and not very big. Okay, so this is just some experimental evidence for that. And so this is in line with the Lindelof hypothesis, which states that the zeta function is bounded by basically t to the epsilon for any epsilon positive. The Lindelof hypothesis is known to follow from the Riemann hypothesis, but we don't really know how to prove the Lindelof hypothesis. Okay, so some progress that we've made towards it is in the form of moments. So a lot of my talk will be about moments of the zeta function and other types of L functions. So going back to ancient history, Hardy and Littlewood bounded the second moment, or actually found an asymptotic for the second moment back in 1918 of the size t log t. And then not too much after that, Ingham got an asymptotic for the fourth moment, which is of size t log to the fourth of t. And I actually, when I was preparing this, I asked ChatGPT to tell me who proved this, and it was very confidently gave me the wrong answer. So don't trust it for these kinds of things. But okay, anyway. So that's the second, that's the fourth, and we're completely stuck on the sixth. And we've made, so we don't know the sixth. So the story sometimes stops here, but of course, there's more slides to come, so obviously I have something to say. So why might we care about moments? So one reason is these can tell us about the frequency of large values of the zeta function. So let's define this function m of tv to be the just the measure of the set of t's where the zeta function in absolute value is at least v. So if v is kind of big, then this is just measuring, how often is it big. So you can use this Chebyshev's inequality to get a bound on this tail measure using the second moment. It's just a really simple inequality. So you can do this for both the second and the fourth moment, and this gives us some sort of tail bound. So if v is sort of big, and we can say that the zeta function rarely takes values of that size. Okay, yeah, so this is what I just said. So these large values are rare. Okay, so then in terms of just the maximal size, we know, so there's what we call the convexity bound, or the Fragment-Lindelof convexity principle tells us that the zeta function is at most t to the 1/4. This is a pretty general statement that holds for other types of L functions too. And so this is what we consider the trivial bound. It's something that just comes from complex analysis. So the first improvement on this is by Hardy and Littlewood. So they use this Weil differencing method applied to the zeta function, and they got this bound of size t to the 1/6, which is now called the Weil bound because it uses Weil's idea. And there have been many improvements to this bound, and the current record is due to Bourgain. Although I didn't write down the exponent. Maybe it's 11/48, is that right? There's too many. I decided there were going to be way too many fractions in this talk already, so I was going to try to reduce that a little bit, but I'm sure you'll agree by the end that there's fraction overload here. There was a t-shirt I saw that just said, it's kind of an anti-math t-shirt, but it just says, fractions. Why did it have to be fractions? And I should have worn that if I had it, but I don't. Anyway, okay, so we can actually use moments to do some of these subconvexity bounds. So one version uses a short second moment of zeta. So this is, again, this was sort of hard to find, like the actual history on this. So there's a formula due to Atkinson from 1949, which gives you this sort of exact formula for the second moment of zeta, transforms it into something else. And then Heath-Brown derived from that this bound. So on the scale of t to the 1/3, we've got sort of the Lindelof hypothesis on average. So that's something that Heath-Brown did. And then Ivanitz did a similar type of result for the fourth moment of zeta. So it's a higher moment and it's a longer interval of size t to the 2/3. And kind of curiously, both of these bounds, if you sort of use them to deduce a pointwise bound, they both give you the Weyl bound back. So this exponent, this Weyl exponent 1/6, we get in different ways. So it's a reoccurring exponent. So they imply this subconvexity bound, but they actually give you more information than that because it says something more about the frequency of large values. There are some results on higher moments. So there's a result on the 12th moment of zeta. It's not Lindelof. It's not sort of what you would get by plugging in Lindelof. It's not t to the 1 plus epsilon. Instead, it's t to the 2 plus epsilon. So Heath-Brown proved this in 1978, and he used that short second moment result that I just had on the previous slide. And then shortly after that, there's another different proof of the same bound of the 12th moment by Ivanitz using the generalizations or cousins of this short fourth moment. Again, that was on the previous slide. Okay, so the 12th moment you can interpolate using Holder's inequality, the fourth and the 12th moments, and you get something about the sixth moment. What you get, if you do that, if you do the exercise, you get exponent 5/4. And that's the best that we know about the sixth moment of zeta. Okay. So now, for a lot of my talk, I want to talk about analogies. It's not really about zeta, but so I want to talk about sort of GL2 analogies. So let's say we have a Hecke cusp form. Let's say for a congruent subgroup, we could just take SL2Z for this talk.
Can I ask a question?
Yes, please.
Before we move to the.
Yeah.
So for the zeta function of a smooth projective curve over a finite field, where we know the Riemann hypothesis, are there results for all the moments that you are satisfied with, or are there conjectures about the moments?
I believe so. But it's not my area of expertise. But yes, there are lots of results about.
Is there a linear
function
type?
Yeah, and there's lots of results about moments in function fields.
It's a massive industry.
Yeah.
Probably the best way to say. I think we'll say.
Yeah, you can talk to me about it after. Yeah, okay. The results about moments that are known over function fields are not strong enough to deduce the Lindelof hypothesis. So we do know the Lindelof hypothesis, but moments in terms of like actually getting the asymptotics by moments seems to in function fields be a much harder problem. And that was, there's conjecture. I mean, so both number fields and function fields, there's lots and lots of conjectures, but the theorems are not that much more advanced. Some are known over function fields, not over number fields, but the theorems are not that much more advanced. And so, so in particular, like this idea of, oh, you get the moment, then you get Lindelof, it's kind of reversed in quantum theories.
Although the Riemann hypothesis is known.
Yeah, the Riemann hypothesis is fine.
That's not helping, yeah.
Yeah, and so you get, well, you have upper bounds for moments from the Riemann hypothesis, but actually getting the exact value is still very, very hard, but upper bounds are okay.
Thanks.
Sorry.
No, that's great, thank you. So, yeah, so the bonus, any questions, just cut out like technical stuff at the end, so it's totally fine. So, okay, so we've got, let's say we have a GL2 cusp form. So this is, and then let's write its Fourier expansion or the Fourier coefficient as lambda f of n. I've scaled it, so I've pulled out this factor n to the kappa minus 1/2. And then that is just so that the Deligne bound says that these lambdas are bounded by the divisor function. So they're that's just the scaling. It's like the correct scaling. So then, okay, so then you can write down this Dirichlet series. You just take these rescaled Fourier coefficients and you get a degree 2 L function. In a lot of ways, it's sort of similar to what happens if you just take the coefficients to be the divisor function. And then in that case, that's you get the zeta function squared, and that's the L function associated to a certain Eisenstein series. So zeta squared is like Eisenstein series, and then you have like these irreducible degree 2 L functions associated to cusp forms. And so there's an analog of Ivanyitz's fourth moment result, which is a second moment for a cusp form. So if you formally take F to be an Eisenstein series, then this thing that I have right here, this is zeta to the fourth. And then if you do that, then this is like exactly Ivanyitz's result, but this is for a cusp form. And Anton Good showed this back in 1982. Okay, so there's lots of these relatives is the point that I'm trying to make. So then similarly, everything that I was talking about, like with the sixth moment of zeta or higher powers of zeta, we can think of as L functions of certain higher rank Eisenstein series. So in this case, the main topic for today will be GL3. And so then we're interested in L functions associated to GL3 cusp forms. And then that's kind of like if you replace this cusp form by an Eisenstein series is like zeta. It's just an, I mean, for this talk, it's just an analogy, but okay, so then, so what's an example of a GL3 cusp form? So the simplest example to give is a symmetric square lift of our GL2 cusp form. You basically are sampling the Fourier coefficients at squares. And this gives you this degree 3 L function, which is known to be automorphic. And yeah, and just for fun, I plotted one of these. So so the LMFDB, the L function modular form database, has GL3 L functions in there, and I just found the first one in their list, and it's just some numbers, and so these are some of the Dirichlet series coefficients. This is the gamma factor. This is not a symmetric square lift, but for a symmetric square lift, this middle one would be 0. And
It's strangely close to 1.
yeah, I think that's the way they
Order it.
ordered it somehow. And actually, there's no symmetric squares in their list that I was able to find, which should be like the first ones they had on there, but
Maybe they removed them, knowing that they're gonna be there.
well, eventually, I mean, you should be able to construct them this way, but they didn't. They're not in the database as far as I can tell, but I'm sure. I mean, you can work with them, so I don't know why they're not there yet, but it's a work in progress, I assume. Okay, so here's the analog of the Z function, and it's kind of similar to the one for zeta. It's not symmetric anymore, and that's because this is it's not a self-dual L function, so the functional equation is not saying that this function is even. Yeah, so anyway, so that's just a new feature here. So now I can state the main result I want to mention today. So this is our theorem. So you take a fixed GL3 cusp form for SL3Z. You can just, if you like, you can mostly think of it as a symmetric square of, the Ramanujan delta function or something like that. Just fix it once and for all. And so we get a bound. So we integrate from 0 to t, and the bound is t to the 4/3. So we think, I mean, we didn't actually check it, but it should be that you can do the same proof with like the Eisenstein series, and so this should prove that the sixth moment of zeta is bounded by t to the 4/3. Which, okay, it's not as good as the 5/4 that I mentioned earlier that you would get by interpolating the fourth moment and the 12th moment. But on the other hand, if for a GL3 cusp form, you don't have those tools available, so we don't. So okay, so it's not new for the zeta for the zeta sixth moment of zeta, but it is new for this GL3 cusp form. And it's a different proof of this bound, so it's anyway, so it has a different character to it.
There's no comparison to Eithbrand's 12th one.
Right.
Any through these reductions.
Yeah, that's right. Because they, I mean, Ivanits's, I mean, you might try to generalize Ivanits's approach. Yeah. Because he has fourth power, so you might be able to put in a GL2 and that's like a square, like Anton Good's result, but something like that. But yeah, we don't have these lower moments to work with. This is sort of the lowest we can do anything with. Okay, so just to sort of, judge the quality of this result. So the zeta function, the analytic conductor of zeta is basically t. The analytic conductor of zeta cubed is like t cubed, and similarly, if you take a cusp form on GL3, the analytic conductor is like t cubed. And so the convexity bound, the convexity bound is always the conductor to the 1/4 power. So here, so here our exponent is, so this 4/3 translates to giving a bound conductor to the 2/9. And 2/9 is less than 1/4. So this is the subconvexity bound for this GL3L function. So just as a baseline, there's a mean value theorem for Dirichlet polynomials that you can always apply. And for GL3, it gives you this bound t to the 3/2. That's sort of like what you should consider the trivial bound on this moment. So 4/3 again is less than 3/2. Okay. So our work sort of builds on or begins with some recent work of Keshav Agarwal, Leung, who's also the co-author on this paper, and Rita Bratamunchi. So they studied the short second moment. And so they can, again, there's so many exponents, I'm sure it's easy to get lost, but so they can have something of length t to the 2/3, and they get this 5/4 bound. So it's a much shorter interval, but their bound is a little bit better. So this gives you, so if you deduce a pointwise bound from this, you get this exponent 5/24, and that's the best subconvexity bound we know for GL3.
Is there a reason this matches the sixth moment bound for zeta?
I don't know. Yeah. But then there was some period of time where we were hopeful that we were going to get 5/4, but then it didn't work.
You said there are a lot of fractions, but there aren't that many fractions with small denominators.
That's true. It's a lot of small numbers. So I don't know. Yeah. And so, so our work builds on their method, but simplifies it I think in a lot of ways. And so I wanted to sort of state like what their result actually looks like. So I simplified it on the previous slide, but what they actually state in their paper is this expression that has these 4 terms, and it has some features that I personally found puzzling. So just my own intuition on this type of thing is that there should be like a diagonal term that's like delta of length delta, because that's sort of the measure of the set that you're integrating over. So you should have a term like delta. And then usually what happens is then there should be some kind of part that decreases with delta. So it's like you have an increasing term and a decreasing term. The diagonal term is increasing in delta, and then these like off diagonal terms are decreasing in delta. And here we have this thing that like 3 of these terms are increasing in delta, but not linearly in delta. one is decreasing in delta. I don't know, I just found this puzzling. I wanted to understand what was going on. Also, if you just take delta equals t in their result, you get something worse than the mean value theorem, like you get something worse than the trivial bound. So I thought that was surprising. I thought that, you know, longer moments should give you better results. Like it should be, I mean, obviously you're integrating over a bigger set, so your answer should be bigger, but it should be sort of easier to work with a bigger family. So I was confused by the method. So yeah, so this project started last year at, we were all at Texas A&M and Joseph presented this work and we wanted to understand it better, and we started working on this long interval version, and this paper was the outcome of that. So there's one result subsequent to the short interval bound due to Samperna Paul, who showed so you got something's a little bit better than the trivial 3/2 exponent. So this is so he saves 3/88. And again, it sort of builds on the other work, but in a, I don't know, it uses different ideas, it's sort of different than what we're doing. Okay, so so I wanted to talk a little bit about the history of GL3 subconvexity. It's sort of a short history. So the first results of any GL3 subconvexity bound is due to Xiaoxing Li in a paper published in 2011. And the way that she attacks the problem is she looks at a certain moment. So it's actually a first moment of GL3 cross GL2 L functions, where the GL3 is fixed and you're averaging over the GL2. And then there's this integral component to it, which is sort of the continuous spectrum or Eisenstein series component of this moment. And so this first moment, this is a GL3 cross GL2, so it's a degree 6 L function. And these values are known to be non-negative. And so so by getting this bound, she could drop all but one term. And this was a big breakthrough. It gave the first subconvexity bound on GL3, although it only works for symmetric squares. So it's only for symmetric squares that the central values are not negative. And then in 2015, Rachel Brattamanci used a different approach, not using a moment, where it sort of breaks down because we don't have this non-negativity anymore. And he used this sort of delta method approach that many people are working on. We had a workshop on this at AIM last fall that some of you were at, and yeah, and so that's an active area of research. So okay, so various people have sort of refined or taken Xiaoxing Li's method further, and so the most recent works in this direction are, so there's a paper by Yangxiao Lin, Ramon Nunez, and Zhi Qi, and then a subsequent paper by Peter Humphreys and Rizwan Khan, and where they worked out this spectral reciprocity formula that has also become a very popular area of research, where you compute start with a moment of one shape and do a whole bunch of things, and then at the end you have a completely different moment. And in this case, so they start with this first moment of these degree 6 L functions, and then you end up with this factors as a degree 1 times a degree 3. So now it's a completely different family of now it's a degree 4 total. And okay, so they transform this original moment to this dual moment. And then so then the game is, well, how do you bound the dual moment? And so now there's a pretty easy approach to this now using our second moment bound. So this we can just plug in. You can use Cauchy-Schwarz on this product, and okay, I have it on the next slide. But basically, you can bound this using our theorem, and as a corollary, we can prove the Lindelof on average bound for Xiaoxing Li's moment down to size t to the 1/7. So this little slide explaining this. It's very simple. You just take this product of these 2 degree 1 or 1 degree 1 and 1 degree 3 L function, just use Cauchy-Schwarz. For zeta, we have this ancient Hardy-Littlewood bound, and then for the second moment of symmetric square, we can plug in our theorem, and you get something that way. And it has this feature that there's okay, I didn't write the diagonal term, but there is a diagonal term that grows with delta. And then this term decreases with delta. This sort of fits with my intuition on how this should work by, that's just a general thing in harmonic analysis. Okay, and so you just choose delta so that these terms are balanced, and that happens to occur at t to the 1/7. So then you input that back into this problem, and this actually gives you a better subconvexity bound for symmetric square L functions on the critical line. So yeah, so there's this nice corollary. It wasn't really why I was originally interested in the problem, but it turned out there were some nice corollaries to the theorem. And there's another one I want to mention in just a moment. And just as a side comment, I have to mention, so there's still, so if you heard about, these subconvexity bounds for symmetric square L functions, there's still a big open question is how to bound this at a half, but as F varies in different families. And then that's needed for the QUE problem. Okay. So another corollary is to what's called the Rankin-Selberg problem. So there's a result back from 1940 where Rankin and Selberg independently proved this famous result about summing up the squares of the coefficients of a GL2 cusp form. And so you get a main term of size x, and then an error term. So the error term that they get is 3/5, and that basically was not improved until just a few years ago. Bingrong Huang improved on this slightly to get this 1/560 using some ideas from like some of Wunsch's delta method ideas. So okay, so we actually can get as a corollary to our theorem, we can improve this to exponent 4/7. And it's a pretty simple method. So there's a standard approach to, if you have a sum of arithmetical functions, you just use like a Perron type formula to convert it to this integral. Now, in this case, this will be the Rankin-Selberg L function, which just like the previous one actually factors a zeta times symmetric square. And then you want to bound that on the integral of that on the half line. So it ends up being essentially the same problem as back here where we have this zeta times symmetric square integrated on the half line. It's kind of interesting. Okay, where did we go? Yeah, so you just do the same thing as we did in the previous corollary and you get 4/7. So I have a slide on this, but I'm just going to skip the details.
How does this compare with what's in Titchmarsh for the event to a power? Not the event, DK event.
DK event.
Should be an Eisenstein there. He's got a whole chapter on this.
So does he? Okay, I forget. I mean, I have to imagine like that's the same as what Rankin-Selberg gives for.
Well, I think if you like, this is the error term in. The positivity is one thing. It's like, it's more like a circle problem at some point. Anyway, he's got this divisor problem that he discusses the remainder term.
Right. So I mean,
he's not doing anything fancy.
Right. I think you just do this, but instead of going to the half line, you shift it past to the left of 0, apply Voronoi, and then just use stationary phase and.
Yeah, that's what they do.
Yeah.
I think.
Right.
Yeah. Anyway.
So.
It's always good to test against.
Right. Yeah, I mean, my intuition is that like that was essentially the same technique that gives you the Rankin-Selberg exponent. So that seems like this, yeah. But maybe it's slightly different because this one factors as degree 1 times degree 3, and so it might just be degree 3. So, okay, so I have some words or overview of how the proof goes. So our starting point is to use an approximate functional equation for our L function. So so it's a general thing that if you have an L function, you can write a value of it as really there's two sums that would both have length square root of the conductor. So in this case, the conductor is t cubed, and so the square root of the conductor is t to the 3/2, and that's what the sum is. So there's really two sums, but they're both basically giving you the same sort of thing. So I'm just writing the first one here, but in practice, it's actually two sums. So we're going to plug that in and then square it out, and we have to do this integral. So we've got this integral from 0 to t, but we should put in a smooth weight function. And so if you do that, then the key thing that you have to do is actually perform this integral, which is, so you have like an m to the it and then an n to the minus it, and you have to integrate that over t. And that's just, you just change variables, and this is t times the Fourier transform at t log m over n. And then, w is some fixed Schwartz class function, and so is w hat. And so if m and n are not too close, like if m over n is not close to 1, then w hat of t log m over n is going to be tiny. So this is a way of saying that m and n have to be close to each other. And the way to quantify this is you just say, okay, well, just sort of take a power series and expand log around 1. And so basically this says that m minus n over n, or just m minus n has to be like at most n over t. And n must t to the 3/2, so this is like square root of t. So m and n are like close, but not, super close. It's not just like, t to the epsilon or something. It's t to the 1/2. So, okay, so if you just do those two like completely standard first steps, you get this expression for the second moment. And so just to remind you, so lambda f of n, those are the coefficients of the GL3 cusp form, which are like more complicated versions of the D3 of n. Okay, so the sad news is like we don't know how to solve the shifted divisor problem for D3. Like we don't know how to get an asymptotic or get a bound on, okay, we can bound this, but we don't know how to get an asymptotic for D3 of n against D3 of n plus 1. And like, we've been stuck on this forever. Okay, so we don't know how to solve this for lambda f of n times lambda f of n plus 1 or any given fixed k. So somehow if we're going to do anything on this, we have to use this averaging over k. So I'm not claiming that we have something non-trivial, like some cancellation in these shifted sums. Okay, so one of the main tools we're going to use here is this delta method of Duke, Friedlander, and Ivanitz. So I'll try to explain what that is if you haven't seen it before. So this is so it's a kind of harmonic analysis way to detect that an integer is 0. And so here's a form of it. So there exists a pretty nice function, capital F, supported on x and y both big O of 1, and with each of its derivatives bounded. So it's just a nice smooth function. And you can then, so you get a sum of Ramanujan sums. And that's a way of detecting that your integer n is equal to 0. So they developed this method in the 1990s, and they used it in many different problems, and it's continued to be a source of, I guess, I don't know, it's been good. Okay, that was really lame, but yeah, so we've been using this a lot for all sorts of problems in analytic number theory. So the principle is that so the integer 0 is divisible by all integers, but every non-zero integer, for every divisor, it has a unique complementary divisor. And so they use that to sort of detect the integer 0 in this way, and then this divisibility condition they kind of decompose in terms of additive characters, and this is where they get these Riemann sums from. So the out of the box, so to speak, DFI delta symbol would have us pick q squared equals n. So that's sort of the standard choice. How do we see why that's the right choice, or why that's the usual choice? I mean, I guess like if you think of C and D of size Q, then this is like sort of 1, and then this is like Q squared. And so N would go up to Q squared. And so to try to like balance those, you pick Q squared equals N. If Q squared is smaller than that, then it's like the function starts to behave differently. I don't know. That's probably not a good explanation. But but we're actually going to choose it to be significantly smaller than n for this problem. So when you do this, what happens is it makes your weight function more complicated. It makes it sort of I guess oscillate more or have bigger derivatives. It makes the analysis, all the analysis that we're going to do more complicated. So we measure this in terms of the Archimedean conductor, which people use in a I guess in the kind of a more general way than just, well, I guess technically we should say that the Archimedean conductor is the part of the conductor coming from the gamma factors in the functional equation and of an L function. And so here we're this is really just like this function f what does it have to do with L function? Like nothing. It's just some function, but you can measure. There's a way you can talk about what you might call the Archimedean conductor. And what it is, so I have this on this this bullet point here. So what we should do is we should think of like n to the iy, like a harmonic like that, having Archimedean conductor y. And more generally, you might say something like that sort of has a phase of size phi. Should have Archimedean conductor of size, like if phi is of size y and has nice derivatives, then this should be like Archimedean conductor y. And this is sort of like you can think of like if you have a function and you use Fourier inversion on it to write it in terms of its Fourier, write it in terms of the integral of its Fourier transform, then the frequencies go up to y. So the Fourier transform is supported up to capital Y. That's kind of like the same sort of thing. So it's like you can recover your function by a superposition of these frequencies up to y. So it's just sort of a way of like measuring how fast your function oscillates. And okay, so if you do this, the amount of oscillation of our capital F is like n over q squared. This is just from like you sort of look at this and say, oh, this is like C and D go up to Q, so this is like n over q squared. That's kind of the amount of oscillation that you have from that capital F. So if q squared is smaller than n, that means you have more Archimedean conductor. So it makes q smaller, so it makes your moduli smaller. So it makes your arithmetic conductors smaller, but it makes your Archimedean conductor bigger. And usually this is a bad trade-off, but for this problem, it's turns out to be good. And so one of the reasons why this turns out to be good is that so if you have two functions and they both oscillate kind of like y, and you multiply them, they still oscillate like y. It doesn't like go up to y squared or something like that. It's still size like y. But like in contrast, if you have like a periodic function mod q1 and you multiply it by a function mod that's periodic mod q2, the new period is the least common multiple of q1 and q2. And so if q1 and q2 are the same, then that stays the same. But if they're coprime, then it's q1, q2. Like so this is saying like conductors usually multiply. If you have a Dirichlet character mod q1 times a Dirichlet character mod q2, the product has mod q1, q2, and the conductor goes way up. But here, like just like at the Archimedean place, it doesn't really go up. You just sort of take the max of the two conductors. So there's some room, like if you already have some conductor in your problem, there's some room to sort of like shove some of the conductor into that spot without making it bigger. And then the trade-off is then, or the savings is that like your arithmetic conductors are smaller. Okay. So, so that's the I don't know, hand wavy explanation. And so we have our moment problem, and we had this shifted sum, like these are GL3 coefficients, and then now we're just saying like M is n plus k, that's our shifted problem. And then we're plugging in this DFI delta symbol to detect that this integer is 0. And we get this great big expression. If you bound this trivially at this point, you're way off from what you started with. Like there's a big cost to applying this decomposition. And then the usual game is like we try to gain it back as quickly as we can. So in this case, the usual first step is to apply all sorts of functional equations. So here we'll use the GL3 Voronoi formula, first proved by Miller and Schmid. It roughly says that if you take GL3 coefficients against an additive character, it transforms into GL3 coefficients times a Klosterman sum, and then the A, kind of like the I don't know, this A in this additive character becomes a bar, which is the multiplicative inverse side. But just to compare, so on GL2, the Voronoi formula just, you still have the additive character on both sides, but you swap A with an A bar. So this is similar in some ways, but different in some other ways. So for the K sum is kind of like there's no GL3 coefficients there, so we can just use Poisson summation on that variable. Okay, so there's you do all these things. There's a lot of analysis, but
You've got a Klosterman sum there, and
Yeah.
are you ever going to use Bay on it?
we're going to use some Bay bounds, but not on that one. Yeah, there's some other ones that come up later.
So far, no arithmetic other than delta symbol and.
Yeah, we're gonna use the Bay bound at some point. Yeah.
I mean, the only arithmetic is the coefficient still there, but you're gonna treat that as a bilinear form probably.
Yeah, we're gonna get rid of the coefficients almost. Yeah, so we use them for this part and then they're gone.
Okay.
Yeah. So, okay, so yeah, so you do all these functional equations, the dust settles, and you end up with an expression that looks like this. I mean, yeah, I'm trying, I could spend hours just explaining this part, but I'd rather not. I don't think anyone wants to see that. But so this y is the same y as before. It's like the kind of amount of Archimedean oscillation that we had from the beginning. It sort of stays constant throughout the problem. K is our dual variable from Poisson summation, and n prime is our dual variable from Voronoi summation. And then all these lengths of summation follow this. There's this rule of thumb that the product of the lengths, the dual length times the original length is the conductor, or solving for the dual length is the conductor over the original length. And so for n prime, the conductor is the arithmetic conductor, which is q, times the analytic conductor, which is y, and then it's cubed because this GL3, the original length was n. Q times y is n over q, and so this thing becomes n squared over q cubed. So you sort of see like the bigger q is, the smaller n prime is. But maybe you don't want to take q to be square root of n. I mean, we'll optimize it at the end. So yeah, so now we're going to completely give up any properties of these coefficients and just treat this general bilinear form. So okay. So one of the reasons why we want to do this is we'd like to use the duality principle that lets you sort of swap the inner sum with the outer sum, which you can do as long as you're willing to deal with completely arbitrary coefficients. And I should say, so far, like pretty much everything like the sequence of moves agrees with what the previous authors did on this problem when they worked on the short interval. Although maybe there's some parts that become a little bit simpler. So the expressions look a little bit different. But the sequence of moves is the same. So now what they did was, so they used a Poisson summation, but then at some point they keep getting, they have these moduli and they keep applying Cauchy-Schwarz to it over and over and over again. They keep squaring it. And then it's like this recursive Cauchy-Schwarz argument that means that they end up with these really complicated character sums that sort of grow in complexity because it's like this, because of this inductive or recursive Cauchy-Schwarz argument. And so they end up having to use the Deligne bound for these sums in order to get their final estimate. And so just as a remark to sort of track the progress, or maybe like as a sanity check. So if you have this bilinear form bound, by general principles of bilinear forms, like the best estimate you could hope for is this one with this Q. This Q comes from the fact that the Klosterman sum basically has size square root of C, and C is size Q, and then we're squaring it. So that's just the size of the Klosterman sums. And then we have the number of things on the inside, which is n prime, and then plus the number of things on the outside, which is Q times K times Y. And so if you just sort of check what this would imply for your moment, it would give you the Lindelof bound for the sixth moment, or for the second moment of this GL3 one, if we had this optimal bound. So needless to say, I don't know how to prove that, but this is a different way to set up the sixth moment of zeta question. I think Ivich basically did this in a conference proceedings paper. Because he used DFI and he used Voronoi and things like that, but he took Q equals square root of n throughout. Anyway.
Sorry, at the beginning, you were saying that you were looking for a delta T term and the 1 over delta
Right.
power. And so in the previous slide, you were saying they were using iterates of Cauchy-Schwarz and Delino. Is this getting lost? What you would have expected?
I mean, it just got so complicated, it's hard to tell like what happened. I don't know.
But you will see it from your method. You'll see that delta MC that you want.
Yeah, we get a delta. Yeah, we get. I think it's worse than that because we can't even prove that, but we get something that. Yeah, I forget what the actual bound looks like, but it does have the feature. Yeah, it does have the feature one term grows in delta and the other decreases in delta. But yeah, I think.
But theirs also had that feature. They just had 3 different versions, 3 different
Right,
ways.
but they also weren't linear in delta. They were like delta cubed and 5 halves and things like that. Which these things get so complicated. It's kind of hard to say. I don't know. I don't know what happened in their paper. Okay, so this K variable. So we sort of did things the wrong way. So for a long time, we were working very hard to work with the K variable. And then like, after we did the whole thing, we realized like, oh, actually we don't need hardly anything about K. We could just sum over it trivially at the very end. And that simplifies a lot of the arguments. But the main, I guess, okay, yeah, I guess maybe I'll just go into a little bit of the ideas, like kind of the cool things.
Sorry,
Yeah.
you said that you would get the sixth moment or square if that were true. What do you prove about that?
We have a bound. I didn't write it on a slide. It's some bound. And then when
what are you using by the Klosterman sum?
So what we're gonna yeah, so we're gonna use so we're using duality. So we've got so it's gonna look like this. We're gonna use Poisson summation. We're gonna square it out, use Poisson summation and n. And then so when you do Poisson summation on like this product of these 2 Klosterman sums, you get additive characters. So that's what we're gonna use. So that's what this is. You get this product, you just simplify this thing and you have 2 moduli, C1 and C2, and it just looks exactly like that. And then so there's this sort of standard elementary reciprocity formula that lets you flip these the moduli. This is really just the Chinese remainder theorem written in this like exponential character form. So so by flipping we get this NK bar becomes the modulus, and then the C1 down here becomes C1 bar, and you do the same thing with the other on the other side. And so that's the structure of the Klosterman sum that we use, I guess, is that we can do this. And then so we completely change the moduli in the problem. The moduli, sort of the product of moduli here, or the total modulus is basically C1, C2, or the least common multiple of C1, C2. Here it's reduced down to NK. So it's like this really nice feature that it's the same thing that we have in the bar here, so that we get the same modulus in both sides. So that there's this sort of nice compatibility between the moduli. And then also we have this nice feature that, like we have C2, C1 bar and C1, C2 bar, which is basically it just means it depends only on the ratio of C1 over C2 now. And so that's another useful feature. And so what we end up doing is, so we just use harmonic analysis on this expression, convert it back into, so use the fact that this only depends on the ratio. And so we can use like decompose it into multiplicative characters. And then that will separate the variables. So we get chi of C1, chi bar of C2. And then the Fourier transform that occurs here is exactly this twisted Klosterman sum. So we get back to a different Klosterman sum of a different modulus. But it's like it's the Klosterman sum with the character. And so now we're kind of in the end game here. So after you do these steps, we've got a sum that looks like this. The large sieve inequality is just perfectly set up to give us bounds in these kinds of expressions. Although here we've got this g hat of chi, which is this Klosterman sum. So if that wasn't there, it'd be really easy just to plug in the large sieve inequality. We'd like it to be true. We wish it were true that we always have the V bound for these twisted Klosterman sums, but unfortunately it's not always true. So for prime modulus, it's true, but for higher prime powers, it's not true. And yeah, there's various, I guess, errors in the literature that like claim this bound for general characters chi, but it's just not true. I think the first place I know that someone observed this was this book by Knightley and Lee, Andrew Knightley and Charles Lee on the Kuznetsov trace formula. And anyway, but so we sort of know what's going on. So it's the short bound isn't true, but it's usually true. And when it's not, we kind of understand when it happened, like when it's not true. And so so we can still proceed anyway. So the optimal choice ends up being this square root of n over t to the sixth, which is again significantly smaller than square root of n. But yeah, when you do these steps, like you just compute what your bound is, and then that's where this 4 over 3 comes from. So one thing I said was, so we had this k, like this k variable that was, I mean, it ends up being this modulus, but it was, I mean, I guess it's this k. We did try to get more savings with that when we were working on this, and it turned out like we ended up with the same bound in the end. It's just a little funny. So it looks like you get some extra savings from k, and you get a different choice of q. The bounds all look different, but like the final bound in the end is the same. I don't really know why. Our proof only needs this V bound for these twisted Klosterman sums, whereas the previous authors on the short second moment, they needed a lot more complicated bounds on character sums. So that's a simplification. One other thing to say, so if you try to study a variant of the problem where you do Dirichlet twists, so you study the second moment of Dirichlet twists, like if you do prime modulus, then it doesn't work at all. We don't know how to do that, but it looks like it should work to some extent if your modulus factors. And Joseph and Kumar are working on this. And then I have this is a very ill-posed question, but so in our case, for this particular problem, we were able to replace this nice idea that they had, which is this infinite or recursive Cauchy-Schwarz argument. We were able to replace it with a large sieve inequality, essentially. And that was a lot simpler, but I'd like to know, well, for what problems is it better, or can we use this infinite Cauchy-Schwarz argument and get something where like you can't replace it with a large sieve? Or can you always replace it with a large sieve? This is a very vague question, but that's, something to.
Can you recover their results?
What's that?
Can you recover their short interval result with this method? Or?
Yeah, I believe we convinced ourselves that we could do that. Yeah, you don't need to do the Yeah, you don't need, yeah. I mean, it's a variant and we'd have to, you have to, all the parameters are different and we'd have to like do a whole other paper on it. But I think we convinced ourselves that yes, you could do it with the large set instead. Yeah. So, okay, that's all I wanted to say.
There any questions?
Did you use that for a full level SL3Z?
So I use that for the GL3 Voronoi formula. So the GL3 Voronoi formula is written down for more general cusp forms of higher level, but it's more complicated, and so we just took the simplest case.
Gotcha.
Yeah. So I think it should work for general level, but we didn't really think about it at all. Yeah.
No questions?
So this subject's still an art,
Yeah, I guess so.
doesn't become a science yet.
I'm trying.
It's a good way, that way you can always. It becomes a science that dies.
I guess, yeah, ChatGPT. It doesn't know who proved the fourth moment of zeta.
Who did it say?
What did it say?
Clearly not you, or you would have been happy.
No.
That doesn't matter.
Yeah. It's completely wrong. It was very confident. It said like, yes, it was this person in this paper, but then it's just complete nonsense.
So if you ask, did the bound rather than the elusive?
Yeah, I don't know. I mean, I think I just asked it who proved the fourth moment. Oh, okay, so it depends on. I know it wasn't when I asked it.
Yeah. By the way, one comment that I have that you didn't point out is Good's works for a cusp form, say like a holomorphic form with a non-arithmetic group. You can get the same 1/5. It's got nothing to do with arithmetic. And that's a good litmus test of what you input to get it. So in a sense, in GL3, they know a non-arithmetic group. So I'm just making that remark. Goods is a very robust, very little to do with anything bound. So that, which is this bound we talk about.
Right.
Mean square on a short interval.
Yeah, and similarly, the Rankin-Selberg bound is like that works for non-arithmetic groups, right?
No, that's okay. I'll explain to you now. It's exactly the point is you normalize the poles. So if you take the Eisenstein series for a non-arithmetic group, the answer is no. No, there are no cusp forms. I'll explain.
Oh, okay. There might be one.
No, that it's not for the existence. The point is that in the Rankin-Selberg method, you know how to normalize the poles of the Eisenstein series. You multiply it by zeta of 2s.
Oh,
That kills all the poles. Then you can use complex analysis.
I see.
Functional equation. But if I take an Eisenstein series with a non-arithmetic group, it's got many more poles. And you have to multiply by a function of order 2 to kill the poles.
Great, that's thanks to the speaker again.